Hello. In the last video, we looked at Gaussian elimination and Gauss-Jordan elimination, where we used our elementary row operations to reduce a matrix to either reduced row echelon or just row echelon form, and that allowed us to solve our system of linear equations. From this, we were inspired to create a definition for when two matrices are equivalent. So they're equivalent if their reduced row echelon forms are the same. And that gave us a theorem that just like fractions reduce to a unique fraction in simplest form, matrices are also going to have a unique reduced row echelon form to them. So that made us start thinking about what other cool things are there about matrices. That's what algebraists do. They've got their objects, they mess with them, and now they want to find some nifty features. So to help inspire us find some nifty features, I've reproduced our example 10 reduced row echelon matrix that we found. And this solution ended up having two parameters. I think we had W was S and we had Z was T at the end of this problem. And then we were able to solve for X, Y in terms of Z, and V was in terms of W and C. This column was representing our variable V, and then we had W, X, Y, and Z. And I wanted to look at this example because this was our only example we've had with more than one parameter. So I wanted to see if that, if we could identify any patterns. So one thing to look at in this matrix is where our pivot positions are. So we have a pivot position here in row 1, column 1. Our second pivot position is in the second row for column X, and the third is over here. So it looks like we have pivot positions for V, X, and Y for those variables. And the columns where we didn't have any pivot positions were for W and for Z. See a connection over here? So the columns where we didn't have a pivot position is where we ended up having a parameter in our final solution. This kind of makes sense because with this pivot position here, I could define, in this case, Y would equal 2 minus 5Z. All I did here was this should be Y plus 5Z, so I subtracted the 5Z to bring it over, right? So because we had a 1 here as our leading entry, and that's our pivot position, we were able to easily define it in terms of something else. We don't have a pivot position for Z. So we don't have this natural way of finding, a definition for Z in terms of other variables. We could certainly use this equation or this one up here to get Z in terms of either Y or X, but that's not the easiest route to take, and it's not the most intuitive. So this connection with where you have a leading entry and where your parameters are, and in fact, how many parameters you have, is interesting. It's a feature about the matrices that we see. And of course, an example is not a proof, but this sort of lends to our thinking about how we might justify such a theorem or a statement. So we're going to summarize this in a general note, I guess. So a broader, more broadly applied note, and we'll see how that could apply to this matrix here. So what note 4 is going to say is the following. When you have fewer pivot positions than variables, you have infinite solutions. And the solution set will involve parameters. Okay, so let's see what this is telling us. So our pivot positions, those were the columns where we had V, X, and Y. And we had more variables than that. We had 3 pivot positions. So we had 3 pivots. But our original equation here had 5 variables. And sure enough, we had fewer pivot positions than we had variables, which meant there were some variables we couldn't define as a specific number. And that's how we ended up getting our parameters. So that's all this note is saying. When you have fewer pivot positions than you have variables, you're going to have variables left over that weren't defined. They're going to become the parameters, and you're going to end up with infinitely many solutions that way. So when you find interesting things in math, you should probably give it a name, right? We probably want to name these things. So we're going to do a definition where we name not only these sorts of variables that have the pivot positions, and those that don't, but also the number of pivot positions in a matrix is going to be important. So we're going to give that a name as well. So let's write that definition. A basic variable is a variable that has a pivot column. So in our last example, this would have been V, X, and Y. Those were the columns that had a pivot in them. A free variable are the other ones. So free variables is a variable without a pivot column. And we can think of the free variables as the ones that are going to end up being parameters. And then our third definition is the rank of a matrix. So the rank of a matrix is the number of leading entries in a row echelon matrix. That is, right, the number of pivot positions. The notation that we're going to use for this is rank, and then in parentheses, we'll put whatever the matrix's name is. So I'm going to use a capital A to represent a generic matrix. But if our matrix was named B, then we would have rank B. So here we've defined 3 terms. We've defined a basic variable, a free variable, and the rank. Okay, so in order to help me remember the difference between a basic variable and a free variable, remember the free variables are the ones that we defined in terms of the parameters. They are free to be any number they want to be, right? So it's kind of like the independent and dependent variable when you're first learning about like X and Y and stuff, right? So the independent variable is free, it goes out on its own, it can be whatever it wants. So our free variable is the parameter, it can go out, be whatever it wants. The basic variables, they just basically follow along, right? So they follow along with whatever the parameter is doing. So a basic variable may end up being defined to just a number, or you may end up with a situation where it's defined in terms of the other parameters. But it doesn't get to choose who it is. It's going to be whatever it's going to be based off of the parameters or its assigned value. So let's do an example of determining the basic variables, free variables, and the rank of a matrix. So we have this matrix A. It's an augmented matrix for some system. And we are told to determine the rank, the free variables, and the basic variables. So to find the rank, that means we just need to count the pivots. So I'm going to go through, I'm just going to circle the pivot positions. Remember, those are our leading ones. So we have one up here, here, and there. So we have 3 pivot positions, which means this matrix has a rank of 3. So rank A equals 3. Next, we are asked to find the free variables, to identify those. So remember, the free variables are the ones that ended up being parameters. So you can think of that as they're like free from the matrix. They don't have a pivot in the matrix at all. So the only column that didn't have a pivot was our 4th column here. So the free variable is, let's call this x1. So we have x1, 2, 3, and 4. The other variables, they're basic. So we have x1, x2, and x3. Those are our basic variables. And there we go. Not too bad, right? So you just want to make sure that you are paying attention to your pivot positions, and then the ones that have a pivot position are tied to the matrix, so they're basic, and the ones that are free from your matrix, they're free. So there are free variables. Now, as before, after we did some row reduction, we had a theorem based off of that. So we're going to have a theorem surrounding these notions as well, kind of similar to what we were just talking about in the previous note. So let's look at what theorem number 2 has to say. So here's our theorem 2. I've already written it out so we could talk about it a little bit more easily. If you want to pause the video here and write it down on your own, you may, and then resume so we can chat about it a little bit. So this theorem is talking about an m by n plus 1 matrix, which is a little strange. There's a reason for it, which we'll get to in a moment. So we have this m by n plus 1 matrix. It corresponds to a consistent system of n variables, and the rank is going to be R. So one of the things we know already is that this system is consistent. So this theorem does not apply if the system ends up being an inconsistent system. So you gotta be careful about that. The reason we're using m by n plus 1 is because really what this is saying, your system of equations has an m by n coefficient matrix, and then that 1 is the column of the BIs. So that's what all the equations are equal to. So if we want to have n variables, which we do, then that's why we have to add this one to account for that column that we pasted onto the original coefficient matrix. So those are our conditions for this theorem. That's when this applies. If all of this is situated, then if n is equal to R, in other words, the number of variables is the same as the rank, then there is a unique, this should be solution. We're just gonna paste that in, pretend that there was never anything wrong here. So the system has a unique solution if n is equal to R. This means, if we think about what that would mean in terms of our matrix, the rank is the number of pivot positions, and the n is the number of variables. So every variable corresponds to a pivot position. So every variable is defined to be a specific value. None of them are parameters. So when that happens, none of them are going to be able to change. So that's how we get our one unique solution to the system. Now, it's going to have infinitely many solutions if the rank is less than the number of variables. So this was the example we were looking at before, where we had a rank of 3, but there were 5 variables, v through z, right? So our rank was smaller, so we had fewer pivots than the number of variables, and we ended up with parameters. In this case, we're going to get specifically n minus r parameters. And if we think about this, it kind of makes sense because I'm going to be taking the rank represents how many basic variables I'm going to have. Those are the variables that are defined to be something. So the ones that are free, that we don't know what they are going to be however many are left over. So I'm going to take my total number of variables, define the ones that are basic, or subtract the ones that are basic, and that will get me however many parameters we have. So this is a theorem that we're primarily going to be applying. So we're going to look at 3 matrices and determine their rank, whether they have a unique solution or not, and how many parameters they would have. So let's go ahead and do a few. To help us look at this example, I wrote a little cheat code over here. So if I have n equal to r, that's going to tell me I have a unique solution. And if r is less than n, that's going to tell me I have infinitely many solutions with n minus r parameters. This is the meat of theorem 2, so long as all of those conditions are met. In other words, we are m by n plus 1, and we know we are a consistent system. So for this example, they want us to first state the augmented matrix for each system. Then we have to state mn and the rank. And then we have to determine, will the solution be unique? And if not, how many parameters will there be? So let's look at this first example. We'll begin by stating the augmented matrix. So this is going to be 1, 4, 3, 0. Then we just have a 2 here and zeros elsewhere. First part is done. Then we have to determine mn and the rank. Now, in order to determine the rank, we need to know how many pivot positions there are. And in order to find the pivot positions, we generally have to be in row echelon form. So that's sort of a hidden step in this problem that we might miss if we're not careful. So let's write this in row echelon form. It doesn't have to be reduced row echelon. So that means we want zeros below and 1 as our leading entry. So we're cool here. And we don't need zeros above. So really, I just have to transform this 2 into a 1. So because I'm limited on my board space, I'm not going to write the whole thing out. But what I would do is I would do half of row 2. And then that would lead to here, right? So if I did half of row 2, I would end up with just a 1 in that position. So this tells me now that here is a pivot position and here is a pivot position. So that means our rank is going to be 2 because we have 2 pivots. M is the number of rows. So M is also 2 because we have 2 rows. And N is the number of columns excluding the solution column, right? So we don't count this one when we're counting N now. So we're just going to get 1, 2, and 3. So here we have a rank, M, and N. To determine if the solution is going to be unique or not, we need to determine R's relationship to N. What is the rank's relationship to the number of variables? In this case, the rank is smaller than N. So we're in this situation here, where we have infinitely many solutions and n minus r parameters. So it is not a unique solution because we have infinitely many solutions, not just one. And n minus r, 3 minus 2 equals 1 parameter. And that's it for part A. So the other 2 examples are very similar. So why don't you pause the video and complete these steps for those two examples there. The only way you're ever going to get a unique solution is if the rank and the number of variables are the same. So take a couple minutes to do that. I'm going to take a couple minutes to do that, and then you'll compare it to what I got, and we'll see how we did. Yay. Hello, it's the voice speaking out from the void. I had to zoom in a little bit because the matrices got a little bit tiny on the screen, so I'm hoping you can see these okay. In example B, I wrote the augmented matrix, and I was very delighted to have done so because I realized it's already in row echelon form. So unlike in part A, I don't even have to do any row operations. I can find the rank straight away. So I circled the leading entries, those leading ones, and there were 3 of them. So this matrix has a rank of 3. There are 3 rows, so M is 3. And if I cut out that augmented extra column, there were only 5 columns. So there would be 5 variables, which means N is 5. Because the rank is smaller than N, this means that this is not a unique solution. And so we end up with 5 minus 3 parameters, or just 2 parameters. For the third example, I was not quite so delighted when I wrote the augmented matrix because it needed some row reduction. So I got rid of the 1 in the bottom left-hand corner by subtracting row 1 from row 3. Then I got rid of the 1 in the middle of the bottom row by subtracting row 2 from row 3. And I ended up with the matrix there at the very bottom. Notice that I have a nice row of zeros along the bottom. So this is okay. We can do that and still be a consistent system. If I had something like 0, 0, 3 at the bottom, now remember that the theorem 2 would not apply, because if you have 0 equaling 3, that means that it's an inconsistent system. But in this case, it's consistent. It works out. The theorem applies. I circled my leading entries, so there were only 2 of them, so the rank of this matrix is 2. We had 3 rows. We had 3 equations to start, so M is 3. And we had 2 variables, an X and a Y, so N is 2. Comparing the rank to N, we see that they're the same. So this is a situation where we would have a unique solution. Ah, the disembodied voice has a body again, hooray! So in this case, that's going to conclude this video, hopefully not too long. And we only have one more video for this week where we're examining matrices and systems of linear equations. After that, we're going to dig into kind of a new concept where we just look at matrices on their own and how matrices as objects in and of themselves are going to interact. So far, we're still a little bit tied to systems of linear equations. So in the next video, we're going to look at 2 things. We're going to look at a new way of expressing solutions that involve parameters. It's not too intense, don't worry. And then we're also going to be looking at a particular type of system where all the BIs are zeros. So we actually had 2 examples here of that, where we only had zeros in the equals 2 side, as well as over here. So that's going to be a special type of system that may have unique properties that systems like this one, where the numbers aren't all 0, might have. So I'm looking forward to seeing you in that next video, and have a great day.